In this video, you will learn how to find out the capacitance of cylindrical and spherical capacitor. If I know the geometry, that is the length and radius of the cylinder as well as spherical capacitor. Now let us assume cylindrical capacitor with inner cylinder having radius A and a charge of rho L coulomb per meter, and a outer cylinder with radius B and a charge of minus L coulomb per meter. So it's a cylindrical capacitor or coaxial capacitor or coaxial cable, and the length of this cable or this capacitor is L in meter. Now, as the length of the capacitor is L, the total charge on the cylinder, it is rho L into L, that is charge density in coulomb per meter multiplied by length in meter. So this will give me the charge in coulomb. If we have infinite line charge with charge density rho L, then we have studied earlier, at any point P, the electric field intensity here, where the distance of this point P with this line charge, it is R. So in this case, the electric field intensity is given by this formula, rho L upon 2 pi epsilon R AR volt per meter. At a sufficiently large distance R, this coaxial cable or the cylindrical capacitor can be considered as a line charge. So based on this formula, E in terms of rho L, we will find out the potential between these two conductors of this cylindrical capacitor, and we will find out the capacitance C. Now, to know the potential difference, we will evaluate this integral V equal to negative to positive E dot dl. A negative means this is the negatively charged conductor with radius B, and this positive means the positively charged conductor, that is inner cylinder with radius A. So in that case, these limits of integration, they will be B to A, and this E we will substitute here. We are considering cylindrical coordinates here, so this dl we will substitute here dr AR. So carrying out this integral to find out the potential, so we substitute here rho L upon 2 pi epsilon R AR. So this is E and this is dl, that is the differential length in cylindrical coordinates, that is dr AR. Now AR dot AR is 1, so this becomes 1 upon R dr, and rho L upon 2 pi epsilon is brought outside of the integral. So we evaluate dr upon R, and the limits are equal to B to A. So integral 1 upon R dr is integral R equal to B to R equal to A dr upon R. This is equal to ln R with limits B to A. So substituting these limits, we get this as ln B minus ln A. So this is the result of this, and rho L upon 2 pi epsilon. This negative sign adjusted here, that's why it is ln b minus a. This is ln b minus a is ln b by a. So v equal to rho l upon 2 pi epsilon. So I got the expression for v. Now C, that is the capacitance, is nothing but Q upon V. Substituting Q as rho L into L and divided by this V. So this we substitute in the denominator. This rho L cancels, and this gives me C equal to 2 pi epsilon L divided by ln b by a. So this is the formula for capacitance of a cylindrical capacitor or coaxial capacitor or a capacitance of a coaxial cable. Next, we find out the capacitance of a spherical capacitor. So here again we assume there is an inner sphere with radius a, which is positively charged, having a total charge equal to plus q, and the outer sphere of radius b with negative charge minus q. This sphere at long distance can be assumed as a point charge. So for the point charge, if I want to find out the electric field intensity E at certain point P, where point P is located at a distance r. So formula for this E is Q upon 4 pi epsilon r square AR. And this electric field E, it is directed in AR direction. So using this formula E, we will find out the potential V by carrying out the integral E dot dl. And similar to what we did earlier, we will find out the capacitance using this formula C equal to Q upon V. So let us find out the potential V. The potential difference between these two plates, it is given by this integral minus negative to positive E dot dl. So negative means it is the negatively charged plate or a negatively charged conductor at a distance B, and this is plus means positively charged conductor, that is the inner sphere with radius a. So this integral limits, they will be b to a. E dot dl, where dl it is the differential length. Now we will consider here spherical coordinates. So in spherical coordinates, dl is dr ar. Now substituting this E here and this dr ar here, let us evaluate this integral. So this is Q upon 4 pi epsilon r square ar dot dr ar. Ar dot ar, it is 1, and this becomes integral dr upon r square. The other terms Q upon 4 pi epsilon can be taken outside. So it is 1 upon r square, that is integral r raised to minus 2 dr. So solving this gives me integral of r raised to minus 2 is r raised to minus 1 upon minus 1, and the limits b to a. Now I can exchange the order of integration, that is the limits, and adjust this sign minus. So solving this, this negative sign minus 1, it cancels with this negative. So it becomes plus Q upon 2 pi epsilon, and the limits r equal to b to r equal to a. Substituting this here, this gives me Q upon 4 pi epsilon 1 upon a minus 1 upon b. This will be 4. So substituting this C equal to Q upon V, So substituting this value of V here, now this Q will cancel, and rearranging this gives me C equal to 4 pi epsilon upon 1 upon A minus 1 upon B. So we have determined the formula for capacitance of a spherical capacitor with inner radius A and outer radius B. Now let us study some special cases of this spherical capacitor. Now we assume it's an isolated capacitor. So that means it's an inner sphere with radius A and the outer sphere of radius B, we assume it is located at infinity. So substituting B equal to infinity here. Now since the outer sphere is located at infinity, the inner sphere we call it as the isolated spherical capacitor. So let us find out the capacitance of such a system. Substituting B equal to infinity, 1 upon infinity it is 0, so this becomes C equal to 4 pi epsilon A. So this is a capacitance, formula for capacitance if I have a single sphere of radius A and the other sphere it is located at infinity. That means we call this as the isolated capacitor. So C equal to 4 pi epsilon A. Now let us study one more special case. Now we have the isolated sphere coated with dielectric. So this is the inner sphere of the spherical capacitor of radius A and outer sphere it is located at infinity. That's why it is isolated sphere. But this sphere of radius A, it is coated with some dielectric material with permittivity epsilon 2. And outside this coating, it's free space. So this is free space that is having permittivity epsilon 0. So let us find out the capacitance of such a system. So this permittivity epsilon 2, it is up to radius R1. From R equal to A to R equal to R1, it is having permittivity epsilon 2. Outside R1, it is epsilon 0, that is free space. So let us find out the potential for this capacitor by using the formula integral E dot dl. Now this negatively charged sphere, it is located at R equal to infinity, and the positively charged sphere, it is at R equal to A. So substituting this limits here, R equal to A and R equal to B, E dot dl. Now this R equal to A to infinity, we will split this into two parts. Infinity to R1, that is this region, infinity to R1, and R1 to A. R1 to A, that is this region. So this is E2 here in this region and E1 in this region. So splitting this integral into two parts. Now we will substitute value of E2 and E1 and let us evaluate this. So in this region A2 R1, this is E1. So at a large distance R, this can be assumed as a point charge. So E is given by Q upon 4 pi epsilon 2 R square in this region. And outside this region, that is R1 to infinity, it is E2. So for E2, here permittivity is epsilon 0. So this is E2 equal to Q upon 4 pi epsilon 0 R square AR. This is directed in AR direction. Now substituting this E1 and E2 here, this is E2 and this is E1 and this is dl, that is the differential length in spherical coordinates. So carrying out this dot products, AR dot AR is 1. So this becomes integral R equal to infinity to R1. This Q upon 4 pi taking outside. So this is 1 upon epsilon 0 R equal to infinity to R1 and integral dr upon R square, because AR dot AR it is 1 here. Similarly in this case, taking Q upon 4 pi outside of the bracket. So here it is 1 upon epsilon 2. Epsilon 2 is a constant. Taking outside of the integral, it is 1 upon epsilon 2 R equal to R1 to A 1 upon R square, because AR dot AR is 1. So evaluating this gives me this as 1 upon epsilon R1, and evaluating this integral in the same way what we did earlier for spherical capacitor. This is 1 upon A minus 1 upon R1. Now we know C is equal to Q upon V. So rearranging this equation, C equal to Q upon V. So substituting this value in the denominator, this is Q upon 4 pi, 1 upon epsilon 0 R1, 1 upon epsilon 2, 1 upon A minus 1 upon R1. Now this Q cancels, and this can be simplified as 4 pi goes in the numerator. So C is equal to 4 pi and this two terms, 1 upon epsilon 0 R1 and this 1 upon epsilon 2 term. Now we will rearrange this to get some interesting result. Taking reciprocal of this 1 upon C, so 4 pi comes in the denominator and this square bracket goes in the numerator. Now this will split it into two parts in this form, 1 upon C1 plus 1 upon C2. So let us split this in this form. So this term 1 upon epsilon 2 4 pi and this 1 upon A minus 1 upon R1, this is the first term. This can be 1 upon C1 and this is in the form of 1 upon C2. This we represented in this form, 1 upon C equal to 1 upon C1 plus 1 upon C2, where C1 is this term 4 pi epsilon 2 upon 1 upon A minus 1 upon R1. Now this formula, it is similar to the formula for capacitance of a spherical capacitor with inner radius A and outer radius as R1. Similarly C2, this result is similar to the capacitance of an isolated sphere. So this result what we got here, this is nothing but connecting two capacitors in series. So two capacitors are connected in series here, a capacitance with spherical capacitor connected in series and capacitance of isolated sphere connected in series. So this is the capacitance of isolated sphere coated with dielectric. So in this video we have learned the capacitance of a spherical capacitor and cylindrical capacitor and some special cases of spherical capacitor, that is the isolated sphere and the next case, it was capacitance of isolated sphere coated with dielectric.